This is our AP Calculus AB video for section 6.2. We're going to be looking at some differential equations that are involved with exponential growth and decay. So just as a review, we've talked about this several times, but the key step when trying to solve a differential equation, at least in this class, is going to be to separate the variables. There are many differential equations in which the variables cannot be separated, but in our class we're going to be focusing on simply those. So make sure that you look to write down and get that key step going. Okay, so let's review how to do this. We've got a differential equation, y prime equals 2x over y, and we are asked to find the general solution. So if you remember from before, a general solution always involves a plus c being on the end. And so let's take a look at how to do this. The first thing I would do is I would take that y prime and I would turn it into dy dx, and that would still equal 2x over y. And then, as mentioned above, the key step, the first step really, is to look to separate the variables. We're going to do that here. I think in one step, if we just take this proportion here and if we cross multiply it, I think we will have the variables separated. So I'm just going to multiply like this. So it's going to give me y times dy equals 2x dx. And I can see now that the variables are separated. All the y's are on one side and all of the x's are on the other side. Once I've done that, I can find the antiderivatives or the integrals. So I'm going to anti-differentiate both sides. So that's going to give me on the left side 1/2 y, let's try that again, 1/2 y squared. And that's equal to x squared plus c. At this point I found my antiderivatives. I've got my plus c on there. And so my final step now would be to try to solve for y. So I would solve for y by multiplying everything through by 2. So that would give me y squared equals 2x squared plus 2c. And of course we know that 2c is really just some other constant. So if I wanted to write it like this, y squared equals 2x squared plus c, that's okay. Some people would put c2 right here to indicate that it's a different c. I'm not going to get too upset either way. Then my final step would be then to do the square root of both sides, so that would be y equals plus or minus the square root of 2x squared plus c, or c2, depending on how you want to write that. And I've got it, right? I've got the general solution, y equals plus or minus that square root of solve for y, and I've got the solution, the general solution, that would lead back to that differential equation. So we've done that before. We're gonna choose to focus today on how we work with exponential growth and decay with these. Okay, so you've seen growth and decay models before. You've seen it probably in you probably saw it in most of your algebra classes, for sure, Algebra 2 and pre-calculus. So we're going to focus on that here for the moment. Let's take a look at this little statement right here. It says if the rate of change of y is proportional to the amount of y, the differential equation describing this relationship is, here would be one way of putting it. You could say y prime is equal to k times y. Let me make that a little bit better. Times, there we go, k times y. Let's talk about why that is. It's saying that the rate of change, so rate of change would be y prime, is proportional is proportional to the amount of y. So proportional means equals y times some constant of proportionality, and that's what that k is. The k is describing how fast this quantity of y, whatever it happens to be, how fast it's either growing or decaying. So if k is really large, it's going to be growing fast. If k is a really large negative number, then it would be decaying very quickly. You know, if k is maybe just like a fraction, then it would be either growing or decaying slowly. And we have our ways of finding what that is, but y prime equals k times y describes the statement, the rate of change of y is proportional to the amount of y. Another way to write this, the way that perhaps I would write that, would be dy dt is equal to ky. The reason why I would do that is because typically when something is growing or decaying, it's growing or decaying as time moves, right? So once you start an experiment or once something is put into place, time continues on, and as time continues on, you'll see that growth or decay. So typically the function that we're working with, in this case y, could be a lot of other things as well, is going to be differentiable with respect to time, and so that's why I would write dy dt. You've probably never seen that before, maybe you have, but you probably have seen the general solution to this. General solution would look something like this: y equals ce to the kt. This is probably the thing you saw in maybe in Algebra 2 or pre-calculus. Y equals ce to the kt. Another version of this would be, let's see here, what is it usually? I equals pe to the rt. That would be describing continuous compounding of interest. There are other versions of that, of course, but we're talking about exponential growth, or in some cases, exponential decay. So what I want to do is I want to prove that this differential equation up here really does lead to this kind of thing right here. So let's take a look at that proof down below. Okay, so we're going to start off with dy dt equals k times y. We're going to end up with y equals ce to the kt. We're going to prove that this relationship up here comes from this relationship down here. We're going to prove that. So here we go. We've got a differential equation. So to solve a differential equation, our first step is to get all of the variables separated. So all the y's on one side, all the t's on the other. The k is a constant, as I mentioned before. The k is not a variable. So what I'm going to do, I think I'm going to divide both sides by y and multiply both sides by dt. That would give me dy over y equals k dt. Important step, not necessarily an easy step, but some algebra involved there. Like I said, multiplying both sides by dt, dividing both sides by y. A key thought here is the dy and the dt need to always be a part of a numerator. They cannot be part of a denominator for this to work, so keep that in mind as you work to separate variables in situations like this. Once I've separated the variables, I want to find my antiderivatives or my integrals, and so I'm going to do that to both sides. The left side, hopefully we recognize that as natural log of y, and then the right side, the antiderivative of k dt would be kt and then plus c. So remember, k is a constant, so it's like a 3 or something. So the integral of 3 dt would be 3t, just like the integral of k dt is kt plus c. Okay, so we're supposed to end up with this up here. We're not there yet. What I'm going to do next now is I'm going to try to get the y by itself. So I'm going to go e to both sides, exponentiate both sides. So I do that. On the left side, that's going to leave me with absolute value of y is equal to e to the kt plus c. Notice I didn't do e to the kt and e to the c. I do e to the whole side, not e to each individual term. It's mathematically incorrect to do it the other way. One note here, at this point, I'm going to acknowledge that I'm dealing with exponential growth or decay, and so there's no way that I could have a negative amount. And so I'm going to, I think, comfortably drop the absolute values here, simply because the absolute values will not have an effect on the y value, like I said before, because the y value stands for an amount of something, and you cannot have a negative amount. We typically want to be very careful about dropping those absolute value signs because, in other situations it's possible that y could be negative. We'll look at those later, but for now, since we're dealing with exponential growth and decay, I don't think that's something we would need to be worried about. Okay, so we have solved for y, so we do have a general solution, but we don't have this general solution up here. So just a little bit of algebra is what we need to do to handle this. Please remember that whenever you are adding exponents, you are really multiplying your bases. And so we could rewrite this to be y equals e to the kt times e to the c. And we're just basically reversing what you learned back in algebra, which is called the product rule. When you're multiplying bases, you add your exponents. And finally, e is a constant, c is a constant, so e to the c is just some other constant. So y equals c e to the kt. You can see that matches, of course, and hopefully a proof that relationship I told you before is actually true. Okay, we're going to look at one example here of this situation, bacterial growth. It says bacteria grow in a certain culture at a rate proportional to the amount present. So that's a key phrase, at a rate proportional to the amount present. So I would underline that, and let's remember what that means from before. I'm going to use different letters, but what it means is this, dB dt. So that would be the rate of change of bacteria is proportional to the amount present. So K times B. So B stands for the amount of bacteria that's there, and that K is that proportionality constant. And so this is the differential equation describing that sentence right there. Okay, so here's one thing we can do here. It doesn't ask us anywhere to show separation of variables, find a particular solution. It just asks us a question. And so in cases like this where it doesn't use those magical words of show separation of variables, find a particular solution, if we want, we can just jump to the general solution right away. So we could write this, B equals CE to the KT. That would be the solution to that differential equation. And again, if you want to show the steps like we did before, that's great, that's totally fine. But here, because we are not asked to show all those steps, we can immediately jump straight from the differential equation to the particular solution. I think it's very important for us to remember what that differential equation is. You'll find out when you look at the examples coming up that oftentimes you're just going to be assessed on if you understand what that differential equation means and how that all works. So don't neglect that. It's just in a case like this we can jump immediately to the particular solution. Okay, so B stands for the amount of bacteria that's there. C and K are both constants. So let's see what happens here. It says, we're given some initial conditions here. Suppose there are 100 bacteria present initially, and the amount doubles in 1 hour. So this one right here, there are 100 bacteria initially. That word initially is really important. That means when T is 0. I'm going to say when T is 0, there are 100 bacteria. That would be 100 equals C, E, and then K times 0 is just 0. E to the 0 is 1, so 100 equals C. Those of you that remember a lot about the about the exponential growth and decay scenarios you guys had in other classes, you might have picked up on that already, that C was going to be 100, but that's how we can prove it. Okay, and the amount doubles in 1 hour. Okay, so what that means then is B is 200, right? Doubles, goes from 100 to 200, so 200 equals 100 E to the K times 1, because 1 hour has passed for this doubling to occur. All right, so let's solve for K. Dividing both sides by 100, we get 2. 2 equals E to the K, and here is where we need to use some of our equation solving skills. How am I supposed to get that K out of the exponent? I've got to do the natural log. So I'm going to do the natural log of both sides. That's going to give me ln of 2 is equal to K. So I found my K. I can then go back and say that B equals 100 E to the ln of 2 times T. Okay, so this is my particular solution here. I've got all the constants have been found, and so I can now answer the question, how many bacteria will there be in an additional 0.5 hours? Okay, so they're asking how many bacteria there will be, so we're going to be finding B. So I'm going to write B equals, I've got 100 E to the natural log of 2, and then my time, it says in an additional 0.5 hours. So we're already told that the amount doubles in 1 hour, so in an additional 0.5 hours, that's going to be 1.5 for T. I think your calculator is going to be really helpful here, so take a minute, see if you can evaluate this. I will do the same. Okay, so in running that through the calculator, I got B is equal to 282.843 approximately. Of course, I get it that you can't have 0.843 of a bacteria. You either have a whole one or you don't. Nowhere did it say to round to anything, and so we're not going to round. Remember, we're going to use the standard 3 decimal convention here. If it did say round, of course we round to 283, but it doesn't say that, so we're going to leave it as 3 decimal answer, and we've got it. So we'll do a little practicing with this when you get to class. Hope this went well for you. I will see you in class.